Okay, everyone. This is Physics 2111, Rabo Community College, for Thursday, 23rd, March 2023. We're going to talk about potential energy today and the science, the symbol that we use for potential energy is either PE or delta U. And we'll talk about that in a little bit. Of course, it's energy, so the units are in joules. And the best thing or best way to talk about, potential energy is with a roller coaster. So we're going to look at a roller coaster. We're going to have a good time on a roller coaster. Okay. First, we're going to do it with no friction. Okay. And then second, we're going to add friction later. So, excuse me. All right. So here's our roller coaster. This is what it looks like. We start out here at the top on the left side, 0.1. We're at a height. Up here, we've got B and A down here at the bottom. We're at a height in meters. We'll talk about what those heights are in a little bit. I just realized something. Okay. Okay. I just wrote down the mass of the cart. I wanted to get it out of the way of that 0.5. So you're in a cart, okay? I don't know. Think of it like Indiana Jones or somebody where they're going through the mine shaft in the cart, in the mine cart. Think of it like that. 500 kilograms in a cart, plus you or whatever. If you want to be in the cart, that's fine. Okay. So we're going to start at 0.1. We're going to go to 0.2, 0.3, 0.4, and 0.5. All right. We're going to look at all of these. Okay. So, let's get to it, I guess. The first thing I want to say is that the work of gravity. So I'm looking down here at this equation here. So the work of gravity is equal to the force of gravity times the distance, right? And of course, the force of gravity is mass times the gravity. The distance is in the y dimension only. So our distance, it doesn't matter, and because gravity is a conservative force, it doesn't matter side to side what we do. It only matters from there to there, okay? So from point A to point B is all that matters. So when we go to figure out the work of gravity, we're going to come down here and we're going to figure out that work of gravity, okay? Or the potential energy that gravity can have. All right. So let's do it. Let's get in here and start doing this. When we first start out here at 0.1, we've got no motion, and we have nothing. Let me say one other thing first. This y-axis is not just the energy, it's also our height. Okay, so it represents our height. It also represents our energy. And I'm going to do a bar graph for the energies. Okay, so our first energy, we have nothing but potential energy. Okay, the whole thing. That's all, and that's what we start with. Our nothing but our potential energy. So gradually, we're just sitting there, and then gradually that chain, chink, 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 chink. All right, that chain starts to push us forward, and the force of gravity is now able to take hold and start pulling us down the ramp. And we happen to be here. I'll do another one right here real quick for point 3. So we get to point 2, and our potential energy is now less. Okay. Here it's less even yet. And here at point 4, our potential energy in this situation is 0. And then back up here at point 5, we've got a potential energy. Okay? Now, let's do blue. What's the difference? Well, we still have a total mechanical energy, and we always will, especially without friction, of this initial energy. So our initial potential energy happens to also be our total mechanical energy. And what happens when you get on a roller coaster and you start going down? You pick up speed, right? So it's at point 4 that you're going to be going the fastest. And which means that this kinetic energy is greatest. Kinetic energy. Kinetic, oh boy. Kinetic energy, and then a little bit of KE right here. Okay. So, our potential energy decreases, and our potential energy, let's talk a little bit about, excuse me, talk a little bit about that. Our potential energy, let's start with at the very beginning. So we've got our point B at the top, point A at the bottom. Our potential energy is UB minus UA, which would be mgh1 minus mg times 0, because h is 0 at A. That ends up giving us here. You guys don't have something that I do. You don't know that this is point 1. This is H1 equals 25. You know what? I want to do that in black. Okay. H1 is equal to 25 meters. Of course, 0 at the bottom. H2 is equal to 20. H3 is equal to 10. Of course, H4 is equal to 0. And then H5 is again 10. Okay. The other thing that I want to talk about here is how far along the track we are. And we'll put that one in green. And once we start, I hope that's green. I don't know if it is or not. Just forgive me. So D1 equals 0. We're going to go to D2, and that is equal to 20. D3 is equal to 26. These are meters. And D4 is 50 meters, and D5 is 80 meters. So when we start thinking about friction, we'll have that. And let's see what else. I put in our friction. I put in our friction force. Okay, so that friction force is going to be a constant force acting in the opposite direction of our travel. Okay, so now we've got all that information. Let's find out what the work of gravity is. So the work of gravity at point 1. Okay, so let's go back here. At point 1, the work of gravity. Well, has gravity done anything? It really hasn't. It has a potential to do something, but it hasn't done anything. So once the cart gets down to 0.4 and it's down to the 0 meters, well, then gravity has done some work, okay? So at 0.4, we can say that the work of gravity is a positive work. However, at 0.1, which is where we're at, it has done negative work. So that equals negative of the potential energy. Okay? So we figured out what the potential energy is, B, from A to B, and we figured out that that was this. And what I'm saying is this statement right here. I'm just repeating it. So the potential energy, UAB, is positive 1.22500. That means that our work of gravity is negative 1.2. Oh, and that's joules. Pardon me. 1.22500 joules. Okay. So work is for the force. Once you get where you're going, then the force's work is positive. For the force, when you get before you get where you're going, it's in the negative if it's a potential energy. And that really only works with springs and gravity, because those are the conservative forces that we're working with. Okay, let's talk a little bit about our total mechanical energy. Excuse me. Our total mechanical energy, and I've got that written over here to the side, is I use this symbol ETM for total mechanical energy. Our total mechanical energy is equal to the kinetic energy and plus the potential energy. U is equal to PE. Okay, so you can use PE if you want, or you can use U, whatever. That's up to you. I think the book uses U. I like PE because you're writing kinetic energy out. You may as well write potential energy out. Okay, so where are we going with this? Well, we're gonna go for a ways here with this graph. All right. This first part, this bit right here, in the top half, this is sans friction or without friction. Okay, so no friction. And our total mechanical energy with no friction, of course, is going to be equal to our total system energy. Okay, so if we look at this term here, the work of friction, if there is no friction, there is no work of friction, and then therefore you have your energy total is equal to the total mechanical energy. If there is friction, then your energy total is equal to the total mechanical energy plus your work done by friction. And that means that if you want to solve for your total mechanical energy, then you have the total energy, excuse me, minus your work of friction. Okay, so the potential energy is a relative energy. So your potential is equal to a delta U. So what that means is you have to get the difference between the two things, which means you're doing this relative to A, okay? So you've got some B and you're doing it relative to A. For gravity, you want to always pick B to be the high side, okay? When you're doing potential energy, if it can get lower, then it has potential energy, so you want that to be positive. So this is kind of a big deal. However, what if you're in a hole, which can happen? Then here's your 0 point. You're down here in a hole, minus H. Your potential energy is equal to mgh, but it's negative, okay? So you can have negative potential energy. As opposed to a spring, so you can have negative potential gravitational energy. But for a spring, because your potential energy is equal to 1/2 kx squared, it doesn't matter what position you're at, if it's a positive position or a negative position, once you square that, so negative x squared still equals x squared, that's always going to be positive, okay? So for a spring, your potential energy for a spring is always positive. Your potential energy for gravity can be negative, okay? And that would be because you've got UA here and UB down here, okay? So that's how that works. Okay, I think I put that on a test too, by the way, just so you guys are aware of that. So let's do it a little bit. We've got our, we need to talk about the conservation of energy. So I'm going to scroll up here. And we're going to come back to that drawing, so fear not. It's not a wasted drawing. Okay, so the conservation of energy. Set timer for 25 minutes. I forgot to set my timer. So, conservation of energy. I cannot begin to tell you guys how important the conservation of energy has been to physics and continues to be to physics. So, the first thing to know, okay, and these are test questions, I'm going to guarantee it. Physics is the study of energy energy in all of its forms. And I'm just going to say, you guys have heard of Einstein's E equals mc squared and all that other stuff. Well, they didn't figure that out until the 1900s. But we didn't know that physics was the study of energy in all of its forms when they were doing this work. But since we have learned that everything pretty much is made up of energy, that's what physics does. We're studying energy in all the ways that it can produce itself. So this is just one more. We're studying basic ways, and it can get more complicated. And you can start talking about the energy of mass and all that other stuff later on in your life. Okay, so the second thing, there are two fundamental laws at the root of physics. So two fundamental laws. One, the most important, this is the most fundamental law in physics. It's the conservation of energy. Two is the maximization of entropy. So this really, it might show up on a test in a way that is clear, but entropy maximization isn't something that we're going to study necessarily, other than friction is a entropic force, okay? But this maximization of entropy and entropy leads us to time. And I don't know if I gave you guys my talk on time yet, but time is just a measurement of entropy. So this is where time comes from, and it's always positive because entropy is always increasing. So time is the measurement of increasing entropy. Okay. So that leads us to third. Now, I think we've killed it. That's it. So that's how important the concept of conservation of energy is. Okay. So let's have some questions about our, we've got this thing. We've talked all about the energy of this thing. But let's say that we want to know what, and keep in mind, we're doing this without friction, right? So first time through, no friction. Second time through, we're going to do with friction. First time through, no friction. Point 2, what is the velocity? Okay, so you can pause right now and see if you can figure out what the velocity is at that point. That would be great. I'm going to do it for you. And away we go. So I suppose we can call this question A. We want velocity at point 2. What is it? Okay, so we can look at our total mechanical energy, since the energy total and the total mechanical energy are the same without friction. We're just going to look at the energy total mechanical, and we're going to say that it's equal to our potential energy plus our kinetic energy. We know that our potential energy is U, which is mgh2, and our kinetic energy is 1/2 mv squared. That's our total mechanical energy. Okay. Hopefully you guys know that when we went and figured out that the potential energy at point 1, let's just look at point 1 for a second. Okay, I'm not going to scroll back up to point 1. I'm just going to say here is point 1. At point 1, if we look at this equation, there is 0 here, which means that the potential energy is our only energy at point 1. So point 1, it's all U, okay? And that means that our total mechanical energy is equal to 122,500 joules. Okay, so now we know that. We can also figure out what our potential energy is at point 2. So we want U at point 2. Not hard. Let's go back up. We've got all of our data here. So point 2, H is 20 meters. Our mass is still 500 kilograms. So 500 kilograms times 9.8 meters per second squared. And we're going to multiply that by 20 meters. So that's our potential at point 2. Okay, well, I don't know what that math is. Is it 20 or 15? What did I put up here? My notes say 15, and then my other notes say 20. So let's go with 20, and I'll just do this. Okay. So 9.8, enter, 20 times 500 times is 98,000. 98,000 joules. Okay, so what does that leave us if we want to solve for KE? Then, of course, we've got our energy total mechanical minus our potential energy at point 2, and this is point 2. That leaves us with 12250. We're gonna subtract that, so we've got 24,500 joules. Okay, great. 1/2 mv squared equals 24,500. We can now solve that for v squared. Two divided by m, so 2 times 24,500 divided by 500. And then we're going to take the square root of both of these things, giving us that. And of course, that's going to be in meters per second. So our velocity ends up being 24.5 divided by 500, 2 times square root. Amazingly, 9.9 meters per second. Not, excuse me, is velocity at 0.2. So let's blank that one in. 9.9. Okay. V3. We can do V3, and we can do all kinds of other ones. But instead of doing A, B, C, D, E, F, G, all that other junk, we're going to grab the bull by the horns and create a table. So here's our table. We've got 0.1, 0.2, 0.3, 0.4, and 0.5. And then we're going to have, at the top, we've got our height in meters. We've got our potential energy in joules. We've got our kinetic energy. Of course, that's in joules as well. We've got our total mechanical energy, again in joules, and we'll have a velocity associated with them in meters per second. Okay, so let's put in the heights. 25, 20, 0.3, 10, 0.4 is 0, 0.5 is 10. We just did 0.2, so let's come back up here. No need to redo all our work. Our potential energy at 0.2 is 98,000. So 98K. Our kinetic energy we found to be 24.5K. And of course, if you add those together, you should get your 122.5K. Okay. And we calculated what the velocity at that point is, and it's 9.9 meters per second. So we've done one. Let's do 0.1. We don't even have to go up and look. We know that it's all potential energy, so we're at 122.5 kilojoules. Our kinetic energy, of course, is 0. And then our total mechanical, which hopefully will always stay the same since we're not doing friction, And our velocity, we still need that chain to chink us along till it will start rolling. Okay, good. Great job, everyone. Now, our third point, since we're at 10, it turns out that our potential energy, and you guys need to do this, okay? You want to go through and make sure you can fill in all of these boxes, okay? If I were you, I would know how to do that for the test. So, and let's see, we end up with 17.1 velocity. Okay, at 0, it's all all kinetic energy, so we've got no potential. It's 122.5 thousand. 122.5 thousand. And then our velocity is our maximum velocity of 22.1 meters per second. The last one, of course, we're going to end up with the exact same thing that we had at point 3. So this one's easy to fill in. And our speed will be the same. We know there's friction in the world, and we know that we won't be going as fast as that at the end, but we're going to figure out what that is here in a second. We have done nothing but consider one force. So this is all considering one force, and that is gravity. Okay. I think we're going to stop for now, and I need a break. So I'll pick up here in a minute about where we left off here.